Hello students, in this last part of electric flux and Gauss theorem, we will determine the electric field due to a uniformly charged thin spherical shell. What is a spherical shell? A spherical shell is a hollow metallic ball. Here we will consider a spherical shell of radius capital R, which is isolated and given charge small q on its surface. The charge is distributed uniformly on its surface. We have to determine the intensity of electric field due to this charge at different points. So first we will consider when point P lies at distance small r from the center of the spherical shell outside the shell. Means small r is greater than capital R. Here capital R is the radius of the spherical shell. So to determine the intensity of electric field at point P, here also we may have to assume a spherical Gaussian surface of radius small r, so that point P lies on the surface, and we will determine electric flux passing through this Gaussian surface by two ways, one by Gauss theorem and one by definition of electric flux. So first, by using Gauss theorem, we will determine the electric flux passing through this Gaussian surface, and it comes out to be phi is equal to 1 upon epsilon 0 k into q, where q is the charge enclosed inside this Gaussian surface. Now according to definition, we can obtain electric flux phi is equal to integral over the closed surface E dot ds. Now to solve this integral, we must know the direction of electric field and area vector of element ds at point P. Here at point P, E is along this direction and area vector of element ds is along the same direction. So the angle between E and ds will be 0. We will write E ds cos 0. So cos 0 will be 1. It will become E ds. The electric field on this Gaussian surface is uniform. So capital E can be taken outside of this integral. We will get E integral over the closed surface ds. Now we will evaluate this integral. ds is a small area on this Gaussian surface at point P. If we integrate this area on this total Gaussian surface, then it will provide the area of this spherical Gaussian surface. So this distance from the center of point P is small r. Area of this Gaussian surface will be 4 pi r square. This will be the value of this integral. Now we will substitute this value in this place. So we get electric flux phi is equal to E into 4 pi r square. Now we compare equation 1 and 2. So we get E into 4 pi r square is equal to 1 upon epsilon 0 k into q. Now we will solve this equation to get electric field is equal to 1 upon 4 pi epsilon 0 k q by r square. If there is a unit vector along the direction of electric field as n cap, we can write this electric field in vector form as E is equal to 1 upon 4 pi epsilon 0 k q by r square into n cap. If the surface charge density of charge on the spherical shell is sigma, then we can write this charge q is equal to sigma into a, where a is the area which is equal to 4 pi r square, r is the radius of this spherical shell. So on substituting this value of q in this equation number 3, we can obtain electric field is equal to sigma r square upon epsilon 0 k into small r square. Now we will consider another case when this point P lies on the surface of this spherical shell. In this case, this small r will be equal to this capital R. So we will substitute in equation 4 and equation 5 capital R in place of small r. So from this equation number 4, we may obtain vector is equal to 1 upon 4 pi epsilon 0 k q upon r square n cap. Also from equation number 5, A is equal to sigma by epsilon 0 k. These are equations for intensity of electric field at the surface of the spherical cell. Now if the point P lies inside this spherical cell at P dash, so this distance OP dash will be small r. In this case, small r is less than capital R. Now to find the electric field at this point P dash lying inside this spherical cell, we will consider a Gaussian surface of radius small r equal to OP dash. Now we will determine the electric flux passing through this Gaussian surface both by definition and by Gauss theorem. First we will use Gauss theorem. So electric flux passing through this surface phi is equal to 1 upon epsilon 0 k into q, and here no charge is lying inside this Gaussian surface, so q is 0, so electric flux will be 0. According to definition of electric flux, again phi is equal to integral over the closed surface E dot ds, and we will evaluate this integral. This will come out to be E into 4 pi r square as in equation number 2. Now both the flux will be same, so we can compare these equations. E into 4 pi r square is equal to 0, so we get E is equal to 0 because r cannot be 0. So electric field inside the spherical cell is 0 throughout its volume. As we know that electric field is varying with distance, we can plot a graph for the variation of intensity of electric field with distance. Here is the figure which gives the variation of intensity of electric field with the distance from the center of the spherical cell. This r is the distance. Here on this side also distance is smaller. You can easily notice that intensity of electric field inside the cell is 0, and on the surface the intensity is maximum here. And when we go apart from the surface of the spherical cell, the intensity decreases as 1 by r square. So we get a curve like this here, and similarly here also.